Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker, Chapter 14, Part 2, Factorial treatment structure. We're going to do an example. An experiment was conducted to determine the effects of 4 different pesticides on the yield of fruit from 3 different varieties of trees. All right, let's stop for a moment and draw this out. We have 4 pesticides, 1, 2, 3, 4. Okay, so pesticide 1, P2, P3, P4. So note, there are 4 levels of the pesticide factor. All right. And then 3 different varieties of citrus trees. So variety 1, variety 2, variety 3, and so on. Variety 1, variety 2, variety 3. So note, there are 3 levels of the citrus tree varieties. All right. And then we have the situation. Sorry, I was trying to move that over. There we go. At the end of the day, we're going to look at the yield of fruit. So essentially, Yijk is equal to mu ij plus tau I plus beta j plus tau beta ij plus epsilon ijk. Just as a reminder, oh, excuse me, Yij is equal to mu. That makes more sense. Knew I had a mistake. Here we go. So just the overall mean, mu plus tau I plus beta j plus tau beta ij plus epsilon ijk. That's because this mu is the overall mean. The other alternative way of writing this, we're not going to use currently. Okay, so essentially, we have to think about the overall mean, right? Then we'll have the means for each of the levels of the pesticide. We'll have the means for each of the levels of the citrus varieties. Then we'll have those individual, there's 4 times 3, 12 different groups when you think about pesticide and citrus variety at the same time. Okay, so what could we do? Well, we could read in the data, and when you look at this, we have variety 1, 2, and 3. So for each of the citrus trees, right, there are 8 observations, right? Let me just make it a little cleaner. Okay. Across the varieties, we have those 8 different trees, right? And what we have then is that we could get the means of each of those varieties. So here we find that y bar 1 dot is equal to 46.875. Y bar 2 dot is equal to 59.250. And y bar 3 dot is equal to 78.250. Okay, then if we just thought about the overall mean, the y bar dot, 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 that is 61.4583. Okay. We can slice and dice our data in other direction into the 4 groups that we have here. And we get for pesticide 1, y bar dot 1 dot is 53. For our second group, 67.833. For our third group, 51.167. And pesticide 4, 73.8333. And the overall mean that we get here is 61.45833. So it matches what we saw before. Okay, so once again, whether we took the mean of the pesticide or the mean of the variety, we got the same exact value for the overall mean, which should be true. All right, so we can go another step further and we could say, okay, we could reformat our data, right? Where we set up the groups to be all the different treatment groups, right? So we have in row 1, that is variety 1, pesticide 1, right? So if we were looking at our original data, let's look at how many groups we have. We already said it should be 12, but let's just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are the treatment groups, right? You got variety 1, pesticide 1, variety 1, pesticide 2, variety 1, pesticide 3, and so on. So now these 12 different rows represent the interactions, right? And then this is the replications. Remember, it said we have 2 trees in each of these replications. Okay, from here, we could calculate the Yij dots, which essentially is saying, give me the y bar 1, 1 dot all the way down to the y bar 3, 4 dot, right? Because that will give us all the 12 groups. And what we get are the means of each of the rows. Okay. So using the formulas above, we can also calculate the total sum of squares. We know that we have 3 citrus varieties, we have 4 pesticides, we have 2 replicates per group, and we can use the formulas from the previous notes to calculate our sum of squares A, our sum of squares B, our SSAB, right? And then we can paste this all together and create our own ANOVA table, okay? Now, if you want, you can go through each of the steps and make sure that this all makes sense. But in reality, this is a lot of work for something that can definitely be automated, but it's always good to check that you can do it. And so how could we do this? Well, all we need to do is use a few lines of code. We're going to use the lm function in R, and we're going to say that yield, which is our y, yield follows the factor variety plus factor pesticide plus factor variety times factor pesticide for our data set. We're going to ask for the summary. When we do that, we get the coefficients of the model. Okay, so we get our model is y hat equals 44, right? Plus 4 times variety 2 plus 23 times variety 3 plus 8.5 pesticide 2 minus 3.5 pesticide 3 plus 6.5 pesticide 4. Then we have plus 6 variety 2 pesticide 2 plus 13 variety 3 pesticide 2 plus 3 variety 2 pesticide 3 plus 2 variety 2 pesticide variety 3 pesticide 3. All's looking good so far. Plus 24.5 variety 2 pesticide 4 plus 18.5 variety 3 pesticide 4. All right, just double checking. 44, 4, 23, 8.5, negative 3.5, 6.5, 6, 13, 3, 2, 24.5, and 18.5. All right, so this is our fitted model, right? And in these cases, right, V2 equals 1 or 0 if variety 2 is true. So these are all indicator variables. Variety 3 is equal to a 1 or a 0 if V3 let's say if citrus variety 3, so this is else right? And same thing with the pesticides. These are indicator variables, pesticide 2, right? This is a 1 if pesticide 2 is used. Otherwise, it's 0. Same thing for pesticide 3 and 4. So by using this LM model, then all we have to ask for is what is the ANOVA of our fit. And by doing that, we can get the entire ANOVA table. And what happens here is we can see, is the interaction term significant, right? And we find out that it's not, right? There's no interaction term based on the citrus variety and the pesticide used. All right, we could have plotted the data to find out if that's true. And when we look at this plot, right? So this is the first pesticide, the second, the third, and the fourth, right? The green, right? We have the purple line is pesticide is variety 2 of the citrus trees. The green line is variety 3 of the citrus trees. The original line is variety 1 of the citrus trees. And what we find here is that these look like pretty parallel lines. So we're not surprised that there's no interaction term. So a plot can tell you a lot. It can tell you just as much as the ANOVA table. Since these lines aren't crossing, we wouldn't expect there to be a significant interaction between the variety of tree and the pesticide used. But what we do know is that different varieties of trees produce different amounts of fruit, and different pesticides also produce different amounts of fruit. So it is important to know which pesticide you should use, and which types of fruit trees or citrus trees will produce more food. All right, I hope you learned something today in this video, and I'll see you next time.